Hello everyone, and welcome to the sixth topic in the SS2 physics curriculum. Now, in this topic, what we are going to be looking at is the equilibrium of forces. Now, this is a very broad topic, so we'll first look at equilibrium of solid objects, then we'll now look at equilibrium of liquids in week 7, that is topic 7 of the curriculum. So as far as equilibrium of solid objects go, here are the areas we must cover. That is what you must learn in this week's work. You should be able to distinguish between resultant and equilibriant force. There are two things entirely you should be able to tell them apart. Now, after that, you should also be able to explain the concept of equilibrium. That is, what does it mean when we say a particular object is at equilibrium? What does that mean? Be able to explain it with detail. Now, after that, you should be able to explain what is meant by the moment of a force. You should be able to define it. You should be able to state the equation to find the moment of a force and apply that equation to solve multiple problems. Now, after that, you should also be able to state the conditions for equilibrium of a body under the action of parallel coplanar forces. That is, when an object is acted upon by parallel coplanar forces, what will happen? How can that body maintain equilibrium or remain stable? Okay. Now, when you're able to state those conditions, they will lead you to some equations and be able to use them to solve different types of problems, such as finding the weight of an object that is stable or that is at equilibrium when it's under the action of parallel coplanar forces. After that, you should also be able to explain or define the moment of a couple. Now, when we say a couple, there are forces that are acting in opposite directions such that it makes an object to begin to spin about an axis. Okay? Now, those two forces has to be equal and they are in opposite direction. So you'll be able to state that, explain it, and show examples of cases where couples are in action. Okay? After that, you should be able to state the conditions for equilibrium of a body under the action of non-parallel coplanar forces. Remember, in the first case, they are parallel coplanar forces. Now, in this case, they are non-parallel coplanar forces. Then to end it, you have to look at center of gravity of different objects based on their shapes and the likes. We're going to look at when you have a beam. We'll look at when you have a circular disc. We'll look at when you have a hollow disc. We'll look at when you have a lamina of unknown shape. Okay, how you can find the center of gravity. And then you should be able to explain the stability of objects, such as when we look at stable equilibrium, unstable equilibrium, and then neutral equilibrium. You should be able to explain them and give examples of such. Now, these are the things that are contained in this topic, equilibrium of a force. Then in the following week, we'll still continue with this same topic, but looking at equilibrium in a liquid. Is that clear now? So now that we've stated what you should do, please, if you are not yet subscribed to the channel, I would like to implore you, please take a moment of your time, click the subscribe button. And another thing that will help is when you hit the notification bell icon, so that you don't miss any of the videos that we give out as we continue in our gaining knowledge in physics. So ensure that you click the notification bell icon so that you get notified every time we put out a new video. And we are also imploring all of you watching the video to please help us reach many more students like you to continue to get access to the helpful videos that we are giving on this channel by sharing the video. And also encourage them to engage with the video. Like the videos, share the videos, drop comments. If there's something you are enjoying from what we are doing, let us know about it. If there's something you would like us to do, also include it in your comments. And if during your study or during what we are explaining here on this video, you do come across something you don't quite understand and you would like to know more, please ask questions in the comment section. We are always here to ensure that your academic journey is as smooth as possible. You know how we say it now, we are your flawless school too. So please, if you have any question, drop it in the comment section and we'll definitely attend to all of your questions. I believe we are ready now, so let's dive into the world of equilibrium of forces. Let us get into the concept of equilibrium. Now, when we say that an object is at equilibrium, now some might think we are looking at it being divided equally or things like that because we are looking at something that has to do with equality here. But that's not what equilibrium means in physics. Now, when we say an object is at equilibrium in physics, what that refers to is that that object is not accelerated. Now, you're already familiar with the fact that objects want to continue to do what they are doing, that is, remain at one position, that is, remain at their stationary position, or they want to continue to move at constant speed in a straight line unless they are acted upon by a force. So that means until an object is acted on by a force, it does not get accelerated. So when an object is in such a state whereby it is not accelerated, that is, the net force acting on that object is zero. That is, by the time you find the resultant of all the forces, you find out that the effect of all the force acting on the body is zero, then such a body is said to be at equilibrium. Now, let's take that in writing. An object is said to be in equilibrium if it is not accelerated. That is, there is no net force acting on the object. Now, at this level in physics, you know that every object is acted upon by a force. Force of gravity, the reaction from its own weight alone, because the weight drags it to the ground, and then whatever is holding it up will give it a reaction which is equal and opposite, amongst other kinds of forces that we've discussed so far. But yet we see around us objects that are balanced, that remain settled. Like, for example, when you place a book on a table, it remains balanced on that table. When you park your car, it remains balanced in your garage, amongst other things that you keep at equilibrium in this context now. So forces are acting on them, but they do not move. This is because when you look at the net force acting on the object, you find them to be zero. So as a result, they are said to be at equilibrium. Now, here's the twist. Equilibrium does not mean the object is stationary. Okay? So it is either the object is stationary. Now, when the object is stationary, that gives rise to what we know as static equilibrium. Okay? In this case, the object is stationary. You see that now? So in the case when the net force acting on the object is zero, and as a result the object remains in one position, then definitely that object is in static equilibrium. Now, there are other objects that could move and still be at equilibrium. Now, that type of equilibrium is known as dynamic equilibrium. Dynamic or kinetic equilibrium. Now, how do we describe this? This is when the net force acting on it is zero, that is, it's not accelerating. However, it is moving in a straight line at constant speed, or it is rotating about its center of mass at constant angular velocity. So we write object is moving in a straight line at constant speed, or rotating about its center of mass at constant angular velocity. So when you balance an object such that it begins to move in a straight line with constant speed, that is, it is not accelerated. Initial speed and final speed, when you take the difference of that, you get 0. It maintains the same speed from start as it continues on that same motion. Then that kind of object is in what we know as static equilibrium. Now, the same thing applies to objects that rotate about an axis. So if it is rotating about its center of mass, which is the axis in this case, at angular velocity, a constant angular velocity, that is, it is not being accelerated as it rotates in this case. That means that that object is in what we know as the dynamic or kinetic equilibrium. So to recap the concept of equilibrium, we now see that an object is said to be at equilibrium when it is not accelerated, and this is because the net force acting on it is 0. Now, we also know that the object does not have to be stationary. Okay, it can be stationary and it can also be moving with constant velocity. Now, when it is stationary, that is what we know as static equilibrium. But when it is moving in a straight line at constant speed or rotating about a center of mass at constant angular velocity, then that is what we know as the dynamic or kinetic equilibrium. To further understand how equilibrium comes to be, it is important to first go back a bit and revisit our study on resultant force, and then from there we can now distinguish between resultant force and equilibriant force. That way we then get to understand how equilibrium comes to be. Now, I'm not going to bore you by looking at when an object is acted upon by multiple forces. We'll keep it simple and just work with when an object is acted upon by two forces inclined at an angle. Okay, so let's assume that we have an object P acted upon by two forces F1 and F2 such that the angle between them is theta. Now, let's take F1 to this point and let's take F2 to this point. Now you see that the length of the line represents the magnitude of the force, and the arrow shows us the direction of the force. Now, if you recall, when we are looking for resultant force, we use the parallelogram law of vectors, and we say that when two vectors are inclined at an angle such that the two vectors are represented by the adjacent side of a parallelogram, then we say the line drawn, that is the diagonal drawn from the point of intersection of these two vectors, represents the resultant both in magnitude and direction. Now, I hope you recall that. If you don't, please kindly check out our video on vectors. We talked about scalars and vectors in that video, and then we show you how to resolve different types of vectors, multiple vectors, when you have them in the same direction, in opposite direction, when they are inclined at an angle, and even when you have more than two vectors acting on an object. So you don't want to miss that video. Please check it out and ensure to drop a comment and also like the video. Now, to work with this, from what we have learned in that video, you will see that we can complete this to make a parallelogram like so. And we know that this line is similar to this, just as this line is similar to this. This angle here is the same as this angle here is the same as what we have here. Now, to get our resultant, all we need to do is draw a line from this point of intersection to cut this point like this, dividing the parallelogram into two. So that's a diagonal. Now, and the direction will of course be like this, and this will be the resultant. Okay, now we are familiar with how to get the resultant like this, and we can even define what a resultant force is. So to define it, let's recall resultant, let's say the resultant rather, the resultant of two or more forces is a single force which has the same effect as or the forces acting on the object both in magnitude and direction. Now, I hope you recall this. That is, when you have more than one force acting on an object, this object P will not be able to move in the direction of F, neither will it be able to move in the direction of F2. But instead, the effect of these two forces will make this object move in the direction of this R, known as the resultant. And the effect at which is going to move here, that is to be forced to accelerate along this path by the effect of the two of these forces, the combination of the two. And you can get that magnitude by using the parallelogram law of vectors. Don't forget that in that case, it will mean that R squared equals F1 squared plus F2 squared. Now, where this will be theta, then plus 2F1 F2 cos theta. I hope you recall that now. Okay, so when you know how to get the resultant, that means this object now is going to accelerate, right? Now, for it not to accelerate, the net force has to be 0. Now, how can you ensure that the net force on this object is 0? Now, recall, let's assume for some reason that F1 and F2 when combined give you a resultant of say 10 newtons in this direction. Let's just say this is 10 newtons. Okay? Now, if this is 10 newtons acting in this direction, how are we going to ensure that that 10 newtons becomes 0? You know that if a force is acting in one direction, the only way you can reduce the effect of that force is to apply another force in the opposite direction of that. Because it is when you have two forces acting in the opposite direction that the resultant becomes a difference of those two forces. So in order to bring the effect of force on this object P to 0, we have to apply another force in the opposite direction of R. Now, you see this force here, when it is equal and opposite to the resultant, then it is known as the equilibriant force. I don't know if you get what I'm saying. Let me recap so that you understand it clearly. So pay attention. F1 and F2 act on P, giving it a resultant effect known as R. Now, we are saying for learning purposes, let's assume that the value of R is 10 newtons and it is in this direction. If you want to make this object be at equilibrium, you have to apply a force in the opposite direction of R, and it has to be equal in magnitude to R. So that is, you have to apply a 10 newtons in the opposite direction of R. Now, that 10 newtons in the opposite direction of R is what we know as the equilibriant force. That is the force required to be applied to the object such that the net force on the object becomes 0. I believe now you get it. So if we are going to define the equilibriant force, we will say it is the force applied in the opposite direction of the resultant force, and it is in the same magnitude. That is a force with the same magnitude as the resultant, but in the opposite direction. So let's put that down. Equilibriant force is a force equal in magnitude but in the opposite direction of the resultant force acting on an object. Okay, this is just kind of what happens when you try to balance something on the tip of your finger. The moment you do that, you see that a force will try to pull it down, and then you have to apply an equal amount of force in the opposite direction of where the object is falling to. That way, it then does what? Balance it out again. The same thing is what is happening here. Two forces acting on the object, giving it a resultant in this direction. So in order to make it balanced, that is at equilibrium, we have to apply an equal but opposite force to the resultant. Now let's recap the definition. If you're asked to define what the resultant force is, you say the resultant of two or more force is a single force which has the same effect as all the forces acting on the object, both in magnitude and direction. And then if you're asked to define what equilibriant force is, you say equilibriant force is a force equal in magnitude but in the opposite direction of the resultant force acting on an object. Now don't forget that if you have any question on this, you can always drop it in the comment section and we will definitely attend to all of your questions. And please ensure that you are subscribed to the channel. You can quickly do that by clicking the subscribe button, and then when you hit the notification bell icon, every time we put out a new video, you will always be notified. Let us solve this question with our understanding of resultant and equilibriant forces. Now in this question, we see two forces 20 newtons each are inclined at 120 degrees to each other, and we are to find the single force that will A. Replace the given force system, and then B. Balance the given force system. Now if you are very clear on the definition of resultant and equilibriant force, then that means that you understand that question A is asking you to find what? The resultant of the two forces, and then B is asking you to find the equilibriant. So now that we are clear on that, let us solve the problem. Now to solve the first part, where we have to find the resultant force, we apply the parallelogram law of vectors. So we say r squared equals f1 squared plus f2 squared plus 2f1 f2 cos theta. Now let's put in the values. R squared becomes, now f1 is 20 squared plus 20 squared plus 2 times 20 times 20 times cos 120 degrees. Now what does this give us? R squared therefore becomes 20 squared is 400 plus another 400, and then we have 800 here. Now plus, now what we're going to have here is 20 times 20 is 400. 400 times 2 will give us 800. And then cos 120 will give you minus 0.5. That is multiplied by negative 0.5. Now when you consider what we have here, we now see that we have 800 plus times minus will give you minus. 800 times 0.5 will give you 400 here. So we have r squared equals 400, which implies that r becomes the square root of 400, and that will give you 20 newtons. So the resultant is therefore 20 newtons. Now that we know the magnitude of the resultant, we can then find the equilibriant. So this is the A part. Now the B part, to find the equilibriant, you know that equilibriant force is equal in magnitude but in the opposite direction of the resultant. So we say the equilibriant force equals 20 newtons in opposite direction of R. R being the resultant. So let's just put it as resultant straight. So just like this, we've been able to solve for the resultant in this system of force and then the equilibriant as well. Now let us consider the equilibrium of three forces acting at a point, otherwise known as the triangle of forces. Okay, so let's consider an object O acted on by forces in this diagram here. So let's say this is point O, and then it is acted on by a force in this direction, and then a force in this direction, such that the resultant is in this direction. So this is F1, F2, and then R. Now what this implies is that we're going to have a resultant and a equilibriant force E at this point. So note that R is resultant and E is equilibriant. Okay, now let's label each point. So if this is O, let's call this A, let's call this B, let's call this C, let's call this point, this is O already, so let's leave it at this, O, B, A, C. Okay, so now that we have all of this, now let's try to interpret what this would give us. Okay, we see here that two forces are acting in this direction, F1 and F2, and the resultant acts in this direction. So in order to keep it at equilibrium, this force E is applied in the opposite direction of R. It is equal in magnitude to R, but in the opposite direction. Hence, we have equilibrium. Now, you see, in this kind of system of forces, okay, we can represent it by three forces in the vector diagram shown here. That is, we're going to have this now. Pay attention. You know, this part now, we can represent it like this. This part can be represented like this to form the parallelogram that we are familiar with. Okay. Now we have that parallelogram. So you see, this part, let's keep it such that we have O, B. Don't forget the direction. Okay. Now you see, you know this is force F1. Okay. This is force F1. Now, F2, this would be F2. Pardon me. OB is F2. So F2 here. Now we have F1 here, which is OC. It can also be what we have here at BA. Okay. So we're going to do that like this. And call this point A. And this is F1. Now, the line that joins these two together is R, which is going in this other direction. However, if we reverse the direction like this, then what do we have there? It then becomes what? Equilibriant. Can you see that now? So we have a system of three forces. Now, where we have force F1, force F2, and then we have the equilibriant, which keeps this at equilibrium. Okay? So this system of forces can be represented by just three lines to form a triangle. Now, this is what we know as the triangle of forces. Okay? This is basically what it says. So if we're going to state what the triangle of forces say, we say that triangle of forces states that three forces acting on an object to keep it at equilibrium can be represented in both magnitude and direction by the three sides of a triangle drawn in order. Okay, now this drawn in order part lets you know that you have to understand the direction and the magnitude of all of these forces and ensure that you draw it to scale. That's just what it means. Okay, so whenever you have three forces acting on an object and that object is at equilibrium, you can solve that problem with every other kind of mathematics you know to solve triangles. Like for example, when you have a triangle like this, you can apply the sine rule, you can also apply the cosine rule. And then depending on the magnitude of each of these forces, you can also apply other rules. Like for example, if F1 and F2 are of the same magnitude, you know this would be therefore an isosceles triangle. And then you can solve it the way you solve any isosceles triangle you know, depending on what you have in the question, right? So let us apply this principle to solve a few questions that involve three forces acting on an object and keeping it at equilibrium, so that we further understand how to apply the triangle of forces. In this question, we see that a mass of 2 kilograms is supported by two cords which make angles of 30 degrees and 50 degrees with the vertical. And we have to calculate the tension in the two cords. Now we are told that G is 10 meters per second squared. That is why you see up here we have W equals mg, that is the mass, which is 2 kilograms, multiplied by the acceleration due to gravity, which is 10, and that will give you 20 newtons. Now all we have to do is show the vector diagram and then use that to develop the triangle by applying the triangle of forces. So let's see what we get from that. So let's say this is the object here, 20 newtons, and it is supported by cords like this that makes the angle here is, let's call this one 30 degrees, and let's call the angle to the vertical here 50 degrees. Now remember, we don't know which is which, but by the angles we can find them out. So let's call the tension here, let's call it T2, while this one here, let's call it T1. Okay, we can complete this by applying the parallelogram law of vectors. Okay, now when we do that, it means that the effect of these 20 newtons will be what we have here to the vertical like this. Okay, and this will be the direction. And you see that this one will be what we have here, while this remains where it is exactly. Now here's the part, finding out where the angle will be. If this is 50 degrees, I can then do something like this also, which will mean this is also 50 degrees. Now if this is 50 degrees, remember that alternate angles should be equal. Now this angle here is alternate, so that means this is 50 degrees. And the same thing applies to the 30 degrees here. Okay, and that will mean this is 30 degrees. Now this is what we have as a triangle. Okay, this is 20 newtons. Okay, this is T2, this is T1, and what we have here is 30 degrees. What we have here is 50 degrees. Okay, that means this angle here, we can get it. Now 50 plus 30 gives you 80. Subtract that from 180, which is the sum of angles in a triangle, and we have here as 100 degrees. So let me do the same diagram here, but more clearer now. Now we know that this is 20 newtons. We know that this is T1, this is T2. Okay, now T1 makes 30 degrees with this, while T2 makes 50 degrees with this. It's not drawn to scale, and this is 100 degrees. It is not drawn to scale. Now we want to solve for T1 and T2 according to the question. Now to solve this, we are going to apply the sine rule. So by applying sine rule, now to those who don't know what sine rule says, it says when you have a triangle like this, then A over sine A equals B over sine B, which is equals to C over sine C. So if we apply that here, it means we will have T1 over sine. Now the angle opposite T1 is 50 degrees. equals T2 over sine, the angle here is what? 30 degrees, and equals 20 newtons over sine, the angle there is 100 degrees. And by using this, we can then begin to solve for each of them. Okay, let's start with T1. We equate T1 to what we have here, and then that will mean that if T1 over sine 50 degrees equals 20 newtons over sine 100 degrees, this will imply that T1 is what? 20 newtons multiplied by sine 50 degrees or divided by sine 100 degrees. Now you can solve this using your calculator straight away. You then have 20 multiplied by sine 50, and then the result of that will be divided by sine 100. And when you do that, you should come up with 15.56 newtons approximately. Okay, that will be the value of T1. T1 is 15.56 newtons. Now let's solve for T2. So to solve for T2, I will say T1 over sine 50 degrees equals T2 over sine 30 degrees. Now what this implies is that T2 equals, now we already know what T1 is, that is 15.56 newtons multiplied by sine 30, and then all of these divided by sine 50. That will mean that T2 equals, now let's find that using the calculator as well. So we have 15.56 multiplied by sine 30. Sine 30 is 0.5, and that will give you 7.78. And then we divide that by sine 50. And the final result is 10.16 approximately in newtons. This is to 2 decimal places. So from what we have in this question, we were able to get a triangle that shows both the direction and magnitude of the 3 forces acting on this object. And then by applying sine rule, we're able to find the value of T1 to be 15.56 newtons and the value of T2 to be 10.16 newtons. Don't forget, if you have any question, feel free to put it in the comment section. And we also plead with you that you help us to share this video by clicking the share button. In this question, we are told that a picture of weight 4 newtons is supported by 2 strings as shown below. Now we are to find the tension on the string at A and B if the strings are inclined at 70 degrees to the vertical. Now we can see this as the picture frame, and the weight is 4 newtons as indicated here. This is point A, this is point B, both inclined at 70 degrees to the vertical. Now what that means is that this part is going to be 20 degrees and this part is also 20 degrees. Okay, now when we complete this like this to make the parallelogram law, this will also be 20 degrees, this will be 20 degrees. Okay, and then we can now draw a line like this to represent the weight of the picture itself by turning all of this into a triangle. Now that will mean we have a triangle that looks like this. Now this is where we need to be careful. The direction is important. The direction of the weight is downwards like this, so that is 4 newtons at this point. Okay, we already have this as T2 at its point here, T2. So what we have here would be T1. T1 will also face the direction that T1 is facing here, which is going upward like this, T1. Now we have this part. So we know that this is going to be 40 degrees, okay, because it's a combination of 20 and 20, which ultimately means that this has to be 70 and this has to be 70. So 70 degrees, 70 degrees. So now we have all the angles there. We can now go on to solve for T1 and T2. Now, to solve for T1, we're going to apply sine rule as we did in the last question also. And then we say T1 over sine 70 degrees equals 4 newtons over sine 40 degrees. That means T1 becomes 4 newtons multiplied by sine 70 degrees, all divided by sine 40 degrees. Now we can find the value of T1. Let's just compute all of this straight up with the calculator. So we say 4 multiplied by sine 70, and that gives us 3.7587 and so on like that, and then we divide it immediately by sine 40. So we want to complete all of this with the calculator in one take, and that would give us a final answer for T1 to be 5.85 to 2 decimal places in newtons. We have the value of T1. Now let's solve for T2. Now what we're going to do is we're going to equate the T1 to T2 by saying T1 over sine 70 degrees equals T2 over sine 70 degrees as well. So if you look at this, it's easy to see that sine 70 cancels sine 70. That means T2 equals T1, which means T2 is also 5.85 newtons. So the solution to this question is that the tension in the strings at A and B is 5.85 newtons each. Have you ever been asked to loosen the tires from a car before? Or have you ridden a bicycle, opened a doorknob? All of these examples shows you applying force to a point in such a way that it causes that point to rotate. That is, the force applies a turning effect on that object that it is applied on. Take for example, when you try to loosen a nut using a spanner, you will observe that when you apply the force from your hand at a point that is very close to the spanner, it becomes really difficult to loosen it. But the longer the spanner, the less amount of force you have to apply to loosen such spanner. This is as a result of what is known as the moment of a force. Now, when asked to define the moment of a force, we say that it is the turning effect applied to a point from an axis. Okay? Now, when you have, for example, let's say this is the point you want to apply the force. Okay? And then you have a perpendicular distance from it, and then you apply the force, say at this point. The turning effect it gives it is what we know as the moment of a force. Let's put this in writing. The moment of a force about an axis. Now, when applying this, there's always an axis of rotation, or what we call a pivot. So I can put this in bracket and say about a pivot is the turning effect of the force about the axis, also pivot. And when you're asked to solve for this, we say that the moment of a force is the product of the force and its perpendicular distance from the pivot. So meaning when you apply force F to this object about its axis point A, you see that the distance here can be denoted D. So in this case, the moment of the force, F equals force F itself multiplied by the perpendicular distance D. Okay? So when you're asked to find the moment of a force, all you need to do is multiply the magnitude of the force and the distance separating the point of application of the force and the axis of rotation. So let's recap the definition. The moment of a force about an axis or pivot is the turning effect of the force about that axis. And the moment of a force is a product of the force and the perpendicular distance from the pivot. And that is how we define the moment of a force. Let's now look at the applications of moment of a force. Now, there are quite a number of things that we do that requires us to apply force to a point that makes that object rotate about an axis. And this is how we get the work done. Now, an understanding of moment of a force will let you know that when you apply such force at a distance from the pivot point, you're going to get the work done without applying much force. Now, this is what I'm saying. Take, for example, when you look at doorknobs, you apply a force to it that causes it to twist, that is, rotate about an axis to open the door and close the door, as we see in one of the applications here on the board. Look at it. We are looking at the common applications of moment of a force. So in that point there, you see that when you apply that force, it rotates about the axis and then the door opens or closes depending on what you're trying to do. Now, the longer the handle is, the lesser the amount of force you have to apply. Now, this is because the moment of the force applied there is the product of the force you applied and the perpendicular distance. So you see that when you increase the distance, then you apply lesser force to open or close doors that have a handle. Now, when the door does not have a handle, you have to apply the maximum amount of force to twist that knob. Okay, so this is why you see that most doors are built in such a way that they have a handle. That way you don't have to apply a lot of force to twist it open or close. Now, another common application of moment of a force around us is what we see in the balancing of seesaw. Now, you know that thing where you play on, you have it on an axis like this, a pivot, and then someone sits at this point applying his weight, and then another person at this point, and then they continue to play on it, making it swing about this axis. Now, when you try to balance it, you have to apply a force at a point that will give you a moment that is equal to what you are getting on the other side. Now, I recall watching a cartoon with the younger ones at home, and then in that cartoon, I saw that a father was playing with his children, and then they were on a seesaw. Now, what the father did was he stayed on one part of the seesaw, which forced the seesaw to then tilt to the ground like this. He was resting at this point, and the children could not apply enough force to balance the seesaw. Now, for them to do this, they had to call on other kids to join them. So the more the kids kept coming, the more they applied more force at this point to be able to balance the seesaw. Now, it got to a point where they have to call all the kids around them, and it was until when all the kids got on top of this other side of the seesaw that they were then able to force it to move up and therefore balance the seesaw. So if you also want to play with the seesaw at home, all you need to do is understand that the point you are sitting on the seesaw determines the amount or the effect, the turning effect you're going to put on that seesaw. Now, this is what it means. If you apply the force at this point, you see that the distance from here to the pivot is very little. Okay? So because of this, the turning effect will be small as compared to when you apply to this point that has more distance. Don't forget, moment of a force is what? Force times distance. So if you want more turning effect, increase the distance or increase the force. Another application of moment of a force is in the using of tools such as spanner and wrenches. Now, you may have observed this before, where they are using the wheel spanner to loose the nut around the nut that is on the wheels of a car. Now, what you observe there is that because the spanners are usually small, they always have to apply a lot of force before you can twist the nut open and then loosen it. Now, if you don't want to apply so much of a force, all you need to do is attach a pipe, a longer pipe, to that the wrench that you are using to loosen the nut. Now, when you apply that pipe to it, this is what happens. You have the wheel spanner like this. This is where the knot is, and then you apply this. Now when you add a longer pole to this part, because of this increased distance d, when you apply your force at a point like this, by the time you apply that force, you apply just a little amount of force and it will force that knot that is at this point to loosen faster. So you see there, if you don't want to apply a lot of force to loosen it, all you need to do is just attach a pipe to it. And this is the case you see especially with when people are trying to loosen the knot down the wheels of bigger trucks and even trailers. They have to apply this long pipe to help them reduce the amount of force they need to apply to loosen the knot on the wheels. Now, another application is in beam balances, or what we know as weighing scales. Now, in the physics lab, when you want to measure the mass of objects, we use something known as the beam balance. And it works based on the principle of moment. You see, the beam balance has two pans, like so. Attached to the pans like this. Now, when you place an object at this point, object A, it will force the pan to drop to the ground. Now, to find out the mass of this, you have to apply an equal amount of force here. So, and we have what we know as known masses, B. When you apply a mass B, for example, if you want to measure 1 kilogram of an object, you put a known mass 1 kilogram here. If I put 1 kilogram here, all I need to do is continue to add A until it balances. The moment it balances, I can then know that whatever amount of A that I've put here is going to be equivalent to what I have in the other pan. And using this method, we are able to measure mass and even weight of objects in the physics lab. And it is dependent on the principle of moment. And then finally, another application of the principle of moment is in the using of wheelbarrows. Have you ever looked at why is it possible for you to use a wheelbarrow to carry heavier loads that you will not be able to carry all by yourself? Okay, now when you put that heavy load on a wheelbarrow, recall that the wheelbarrow has a handle that is very long. And when you look at the distance from that handle to the pivot of the wheelbarrow, now in case you don't know where the pivot is, it is at the wheel itself. Look at that long distance you have there. It means you have to apply even less force for you to be able to lift that heavy load that you have put on the wheelbarrow. This is why you can use a wheelbarrow and even a cart to carry heavier loads, because all you need to do is apply a little force, given that you have a long distance between the application of your force and the pivot of the wheelbarrow. So you see here, everything you do that involves you applying force to force an object to rotate about an axis, you can always reduce the amount of force that you apply. All you need to do is just increase the distance between the point of application of your force and the pivot. And that is how you too can apply the principle of moment. Now let us state the principle of moment. You already know that the moment of a force is the product of the force and the perpendicular distance that separate the force and the point of application of the force and the axis of rotation. That is, force times distance gives you moment. But what does the principle of moment state? Because most of the time when we solve problems on moment, it depends on your understanding of the principle of moment, and in some cases also the conditions for equilibrium under action of parallel coplanar forces and then under action of non-parallel coplanar forces. But first, let us look at what the principle of moment states. I'll write it first and then we'll state it together. The principle of moment states that for an object to be at equilibrium, the algebraic sum of clockwise moment about an axis will be equal to the sum of anti-clockwise moment about same axis. Now, what does this mean? It means that if we have an object, let's say this beam A, B, and then it is placed on a pivot like this. If this beam is going to be at equilibrium, that is, if it is going to balance horizontally on this pivot, what must happen? It means that you have to apply a force here and another force here. You can have more than one, okay? You can have more than two, I mean, but I've just drawn these two to explain something here. Now, these forces are applied in such a way that they will make this to rotate about the axis, okay? So let's call the distance here x, and then we call the distance here y, and then we call this F2, and we call this F1. For this beam to be at equilibrium, the algebraic sum of clockwise moment must equal anti-clockwise moment. Now, what is the clockwise moment? We're going to look at which force makes this beam to rotate in the clockwise direction. Remember, the clockwise direction goes like this, okay? So when you apply this force, it's going to force this beam to rotate about this axis in the clockwise direction. So you see the clockwise moment must equal anti-clockwise moment. And that would be what? The clockwise moment is what? F1 multiplied by x. And this has to equal F2 multiplied by y. That is F1x equals F2y. And this is how you apply the principle of moments. Now, it is not always limited to this, which is why in addition to understanding the principle of moments, you also have to understand the conditions for equilibrium, especially in cases where you have parallel coplanar forces and then non-parallel coplanar forces. But before we go on to apply this to solve some problems, let's recap what the principle of moment states. So, the principle of moment states that for an object to be at equilibrium, the algebraic sum of clockwise moments about an axis will be equal to the sum of anti-clockwise moments about same axis. Now, one more time. The principle of moment states that for an object to be at equilibrium, the algebraic sum of the clockwise moment about an axis will be equal to the sum of anti-clockwise moments about same axis. And that is the principle of moments. Let us apply the principle of moments to solve this problem. Okay, it says a uniform meter rule weighing 0.5 newtons is to be pivoted on a knife edge at 30 centimeter mark. Where will a force of 2 newtons be placed from the pivot to balance the meter rule? Now, to solve questions like this, there are a few things we need to understand. You see, in this case, when we say that there is a uniform meter rule, it means that the weight of the meter rule acts at the center. And now, note, a meter rule is graduated from 0 to 100 centimeter, right? So if it is at the center, that will mean at the 50 centimeter mark. That is where the weight of that meter rule is going to act. Don't forget that the weight is what? 0.5 newtons. Okay? Now, we also know that the pivot is going to be placed at the 30 centimeter mark. And we have to understand what this question is saying. It's saying, where will the force of 2 newtons be placed from the pivot? That is, we are going to measure the distance between the pivot and the point of application of the 2 newtons force. So let's draw a diagram to represent this so that it makes our calculation easy. All you need to do at this point is draw a straight line to represent the meter rule. So let's say this is the meter rule. Let's call that AB, where this is the 0 centimeters mark and this is the 100 centimeter mark. Now the center, which is the 50 centimeter mark, will be where the weight of the meter rule is acting downward, and that is 0.5 newtons. Now at the 30 centimeter mark, we're going to apply a pivot like this, and then to balance this meter rule, there has to be a force applied at this point, which we don't know the distance from here to here, and that's what we are asked to find. The distance from the pivot, it means this distance here, we will call that x, but we know this distance to be what? Now if this is 30 and this is 50, it means this distance here is 20 centimeters. So using this diagram, we can then go on to find the value of x, which the question asks us to solve for. Now, let me state this. Some questions will not ask you to find the distance from the pivot, but will rather ask you at what point will the force be applied. So for that one, you have to find what the value of you are graduating the meter rule. What this would read is what we have to find, the reading at this point. And when you find the value of x here, you just subtract it from 30 and then you have your answer in that case. So I'll use this question to explain both of them so that you know what to do depending on what the question asks you to solve. So using this diagram, let's first find the value of x, which is the distance from the pivot that you have to apply the force of 2 newtons. Don't forget the force applied here is 2 newtons. Now, what does the principle of moment says? Principle of moment says clockwise moment must equal anti-clockwise moment for the meter rule to be balanced. Now, what is our clockwise moment? That is this force acting at this point multiplied by the distance. That will be 0.5 newtons multiplied by 20 centimeters. Now we equate that with what we have here, which would be 2 newtons multiplied by x, okay, which is this value here. Now to get the value of x, we say x equals, now the product of this is 10 newton centimeters, so divided by 2 newtons, and then we see the answer is what? 5 centimeters. Okay? So it means that the 2 newtons has to be applied 5 centimeters from the pivot. Now, in the case where the question is asking you to find the point of application, you now say the point of application of 2 newtons equilibriant force is 30 centimeters minus 5 centimeters, and that will give you 25 centimeter mark. So at the 25 centimeter mark is where you have to apply these 2 newtons for this meter rule to be at equilibrium. So I believe you understand how this is applied now. So you see, you can use this not only to find the point of application, you can also use it to find the weight of a meter rule. If you don't know the weight of this meter rule now, and then you apply a force at some point, and then you try to balance the meter rule, knowing that if it's a meter rule, the point of application is at the 50th centimeter mark, you can always find the weight of a meter rule. Let us try to solve a question like that so that you understand how to find the weight of a meter rule using the same method. Let's solve this question from the 1986 JAMB exams. It says a uniform meter rule QR is balanced on a knife edge which is 55 centimeters from R when a mass of 10 grams is hung at P as shown above. The mass of the meter rule is, remember I said we can use this to also find the mass of the meter rule. The same method we used in the last example we solved. Okay, now all we need to do is look at this diagram and put in the details that we can find from this question that are missing in the diagram. Now, the first thing you should know is that this pivot is 55 centimeters away from R. That is, this distance here is 55. Okay? So, the mass of the meter rule is supposed to be acting at this point, right? Which is going to be 50 away from R. So that would mean that if this place is 50, then this place would be 5. Remember, 55. 5 plus 50 is what makes this 55 here. Now, if all of this is 55, then what is left here is going to be 45. And we already have 10 here, so which means whatever is left here is 35 centimeters. Okay? So now that we have these details, we can now go on to apply the principle of moment. Now, one more thing. I understand that many people are easily carried away and they immediately want to start converting units from centimeters to meters, from kilograms, from grams to kilograms, and then to newtons and so on. Yes, it is always good to solve problems in the correct SI unit. But you see, oftentimes the kind of questions you'll be solving, especially in some kind of exams like the UTME exams, SAT exams and things like that, the kind of unit you will be given may not be the SI unit. But when you consider the options you are provided with, the options too are not in the SI unit. So it means that you can easily solve in the unit you are given and then still get your direct answer. Now, in this case, there is no issue because we are not dealing with moment as a vector in this case. We are looking at it based on magnitude, the merit of its magnitude alone. So as a result, we don't need to convert it to newtons. We don't need to convert mass to newtons, that is to weight. We don't also need to convert the distance here to meters. We can work on these same units that we have because they eventually cancel each other out and we have what we need it to be. Okay? So let's go on to solve this problem. Don't forget, the principle itself says clockwise moment equals anti-clockwise moment. So to apply it, our solution will be, now what is our clockwise moment? That will be the product of the mass and this distance. So 5 multiplied by m would give us 10 grams multiplied, remember that this is in centimeters, okay, multiplied by 35 centimeters. So now we have 5 centimeters multiplied by m equals, this two will give you 350 grams centimeter. Now when we make m the subject, we now have 350 grams centimeter divided by 5 centimeters. So easily, you see centimeter cancel centimeter, and then we have mass m to be, now 5 here 1, 5 here 7, here 0, and then that is 70 grams. So the mass of this meter rule is 70 grams. You can try to solve this question yourself. Apply the principles of moment just as it has been taught in the previous examples and see if you got the same answer, if you get the same answer that is gotten at the end of this video. Okay, now the question itself says, in the figure, it shows that a seesaw which is perfectly in balance, and then the weight of people sitting on it are 50 kilograms, x kilograms, and 15 kilograms as shown. And they sit at distances of 1.5, and 2 meters from the pivot respectively, where this is the pivot, and then you have to find the value of x. Okay, remember I mentioned that you can have more than 2 forces acting in the clockwise or anti-clockwise direction. So just apply the principle of moment based on how it was taught in the previous examples, and let's see what you got. Now, this is what your solution should look like. Remember that sum of clockwise moment equals the sum of anti-clockwise moment. Now, for the clockwise moment, we're going to be having the distance multiplied by the mass. So in this case, we have x multiplied by 1.5 meters plus 15 multiplied by 2 meters. And this equals, on the other side, which is the anticlockwise moment, we have 50. Remember, this is in kilograms, okay? Kilograms. So 50 kilograms multiplied by the distance is 1.5 meters. Now let's see what we have. This would give you 1.5x kilogram meter plus, this would give you 30 kilogram meter. And that equals, when you multiply this, what do we have? This will give you 75 kilogram meter. Now, to find x kilograms, we have to collect like terms and say 15x kilogram meter equals 75 kilogram meter minus 30 kilograms meter. Now, 1.5x kilogram meter therefore becomes, the difference here is 45 kilogram meter. Now, divide both sides by 1.5 meters. 1.5 meters. And then you see that x in kilograms equals, now 1.5 divided by this, we can just say the same thing as 450 divided by 15. Now 15 go in 45 3 times, and then we have 0, that would be 30. So that is x is 30 kilograms. So the value of x is 30 kilograms according to the question. For an object to be at equilibrium, there are conditions necessary for that. And now we want to look at the conditions for equilibrium under the action of parallel coplanar forces. Now when we say coplanar forces, it means forces that act on the same plane. Okay, it could be to the x-axis, to the y-axis, but they are on the same surface. And in this time, for this one, we are looking at when they are parallel to each other. So what are the conditions that must be fulfilled for an object to be at equilibrium when it is acted upon by multiple forces in the same plane but are parallel to each other? Now, there are two main conditions for this object to be at equilibrium. One depends on the forces. So condition one is what? The forces. Now, what does this condition state? It states that for an object to be at equilibrium, the algebraic sum of forces, or the net force acting on that object, must be 0. Now, what this translates to is that the sum of the forces acting in one direction on that object should equal the sum of forces acting in the opposite direction. Now, let's put that down. The net force acting on the object must be 0 for it to be at equilibrium. Just like I mentioned, that is the sum of forces acting in one direction equals the sum of forces acting in the opposite direction. So for example, if you have a bar like this, and then a force is acting at this point, say 10 newtons, and then another one like this, 10 newtons. It is pushing it upwards. For this bar or beam to be at equilibrium, there must be another force acting in the opposite direction, which is equal to the sum of these two forces. That is, I can have multiple forces, but the key thing here is that they must all sum up to give you 20 newtons, and they must be in the opposite direction. That is what this first condition tells us. Now, the second condition is on moments. And this is dependent on the principle of moment. And this one states that the algebraic sum of moments about an axis must be 0. That is, the sum of clockwise moment must equal the sum of anticlockwise moment. The sum of anticlockwise moment. Now, these are the two conditions necessary for an object to be at equilibrium when it is under the action of parallel coplanar forces. So a quick recap. The first condition is that the sum of force acting in one direction must equal the sum of force acting in the opposite direction. And the second condition is that the sum of clockwise moments about an axis must equal the sum of anticlockwise moments about the same axis. Now let's apply this to solve problem of equilibrium of objects under the action of parallel coplanar forces. Now let us look at how we can apply these conditions to solve this problem. And this is a problem from the 1979 UTME. It says a uniform beam HK of length 10 meters and weighing 200 newtons is supported at both ends as shown above. So we see that there is a pivot at H and another pivot at K. And then a man weighing 1000 newtons stands at a point P. This is where the man stands on the beam. Now, if the reaction at H and K respectively are 800 newtons and 400 newtons, that is, this reacts upward at 800 newtons and this at 400 newtons. We are to find the distance HP. Okay, so let's interpret this. So we have the beam, okay, where this is H and this is K. There is reaction here, which is 400 newtons. There's a reaction here, which is 800 newtons. At the center point here, which is 5, remember this will be 0, while this is 10, right? At 5, we have 200 newtons acting downward. Then at P here, we have 1000 newtons acting downwards. Now, when you look at this, does this satisfy the condition for equilibrium under the action of a parallel coplanar force? Yes, because we see that the force acting upward, 800 newton plus 400 newton give you 1200 newtons. And it is equal to the forces acting downward, which is 1000 newton plus 200 newton, which is the same 1200 newton. So condition 1 is fulfilled. So we can be rest assured that this object is at equilibrium. So since it is at equilibrium, we can now apply the condition 2 to find the distance. So let's call this distance here x. Okay, so we now say taking pivot at H. At this point now, this 800 newton doesn't act. This other ones then begins to rotate it. So that means this will be our anti-clockwise force and this will be the clockwise forces. So we now do clockwise movement equals anti-clockwise movement, which will mean that we have 1000x plus 200 times 5 to equal 400 times 10. Now, here we have 1000x plus, now when we multiply this will give you 1000 equals, this will give you 4000. Now, collecting like terms, 1000x becomes 4000 minus 1000, and we have 3000. Meaning x becomes 3000 divided by 1000, and the answer is 3 meters. That is, point P is 3 meters away from H. So since the question says we should find the distance HP, our answer is simply 3 meters. And that's the solution to this question. Now let's solve this question. It says a plank AB 3.0 meters long, weighing 20 kilograms, and with its center of gravity 2.0 meters from A, carries a load of mass 10 kilograms at end A. Now it rests on two supports at C and D as shown below, and then we have this diagram, and we have to find the values of the reaction R1 and R2. So let's complete this diagram with the information in the question that are not in the diagram. Now we know that the plank itself weighs 20 kilograms, and the point where that acts, remember this is 20 kilogram now, this is going to be 2.0 meters apart. Okay, so now that we have this part, we can then go on to apply the conditions for equilibrium under the action of parallel coplanar forces. Now in this case, ensure that everything is in the proper SI unit so that you can solve correctly. Now for the first condition, force acting in one direction must equal the force acting in the opposite direction. That means that R1 plus R2, which are the only forces that are acting upward, should equal the forces acting downward. Now this is 10 kilograms converted to newtons. That will be 10 kg times 10 meter per second squares, and that will give us 100 newtons. Plus, this is 20 kilogram times 10, and that will give us 200 newtons. Okay, that means R1 plus R2 equals 300 newtons. Let's call this equation 1. We will come back to this as we go on. Now, to be able to solve one of these, we have to take moment about an axis that is acting either at R1 or R2. Now, I want to solve R1 first. So I'm going to take pivot at D. That way, R2 will not be part of my calculation, and then I can easily solve for R1. So I say taking moment at D. At pivot D, we then do clockwise moment equals anti-clockwise moment. Now at pivot D, you see that R1 is our clockwise moment, and 10 kilogram and 20 kilogram becomes the anti-clockwise moment as they will rotate about D in the anti-clockwise direction. R1 is the only one that goes around D in the clockwise direction. So clockwise moment will then be R1 multiplied by the distance between R1 and pivot D. That is what? 2 meters. Equals, now the sum of anti-clockwise. Now this one is 20 kilogram, which is 200 newtons. That will be 200 times the distance here is what? Now if this is 2 and this is 0.5 and this is 2, which is 2.5, from here to here is 2.5, and we have taken 2 out of it, we are left with 0.5. So 0.5 plus, now this is 100 newtons multiplied by 2.5. Now let's see what this gives us. So 2R1 therefore becomes, this would give you 100 plus, this would give you what? 250. So that means 2R1 equals, when you add this, we have 350, which implies that R1 is 350 divided by 2. So R1 would give us 1. In 15, that is 7. Remainder 1. Then 5. So 175 newtons. That is the value of R1. Now, in order to solve R2, we impute this, we substitute it into equation 1. So sub R1 equals 175 newtons into equation 1. So equation 1 will now be 175 newtons plus R2 equals 300 newtons. That means R2 becomes 300 newtons minus 175 newtons. The value of R2 would therefore be 125 newtons. And the solution to this question is therefore the reaction R1 is 175 newtons, while reaction R2 is 125 newtons. Now, if you do have any question, you can always drop it in the comment section and we promise to attend to all of your questions. And please, if you're yet to be subscribed to the channel, kindly take a moment of your time, click the subscribe button, and then you can also hit the notification bell icon so that every time we put out a new content, you will always be notified. And we are also imploring you to help us reach many more students like you by sharing the video. Please ensure that you click the share button so that you can help many students like you to get access to this helpful content that we are making right here on this channel. Having considered when you have equilibrium under the action of forces that are parallel and coplanar, it is now time for us to look at what if the forces acting on an object are non-parallel yet coplanar. What are the conditions for such an object to be at equilibrium? So the subtopic we are looking at here is conditions for equilibrium under the action of non-parallel coplanar forces. Now, there are two main conditions, just like in the case of the parallel ones, and that is forces and moment. Now, note that at this point, the forces are non-parallel, so as a result, they are inclined at an angle. And when you are dealing with vectors inclined at an angle, one thing you always have to remember is that in these cases, you will have to resolve the components of such vectors either to the vertical or to the horizontal. So let's quickly do a recap for those of you who still don't know how to find the component of a force to the horizontal or to the vertical. It goes like this. If a particular force F needs to be, you need to find the component to the horizontal. The horizontal component is called f of x, and it is given as f cosine theta. And then the vertical component f of y is given as f sine theta. Theta here being the angle at which it is inclined to the horizontal. Now, since we've looked at this now, let's look at how it applies to the forces for a body that is at equilibrium but under the action of forces that are non-parallel and coplanar. Now, the first condition is that the vector sum of all forces acting on the body must be 0. Now, what this translates to is that the body must not be accelerating in any direction, whether to the horizontal or to the vertical. Okay, the body must not accelerate. So the summation of f of x must be 0. That is, when you consider the horizontal plane, the forces acting to the right must balance out with the forces acting to the left, such that the body is not moving either to the right or to the left as a result of those forces. Now, in this case, the forces may not directly be pointing to the left or the right. You have to consider the horizontal component. So when you find the horizontal component and then you sum everything up, it should give you 0. And at the same time, the same body should not be accelerating either upwards or downward. That is, when you find the vertical components, that is f of y, and you find the sum of such, that is those moving upward and those moving downward, should cancel out such that it gives you 0. So summation f of y should also be 0. That is what this first condition states. Now, the second condition is about the moment. And it says that the algebraic sum of the moment of the force of all forces about any axis perpendicular to the plane of the force must be 0. Now, that is if you have the object like so, and then there is a force acting at this point F. You have to resolve this to the horizontal. That is, you have to get horizontal and vertical components of such force so that you will be able to find the clockwise and anti-clockwise moments. Remember, when dealing with moments, we always look at the force acting upwards and downwards, right? So the weight of the object itself will be acting at this point. So let's assume this is the axis, okay? Now, you have to find the vertical component f of y in this case to find your clockwise moment and anti-clockwise moment. This one would be the weight of the object in this case. So that's what this particular condition is stating. That when you find the force itself, you have to look at the components of such force about the axis perpendicular. You see that? Perpendicular means at 90 degrees to the axis. So as a result, you have to find the vertical component rather, in this case. So when you get the vertical component, you can then apply the moment, principle of moment, which says the clockwise moment about an axis must equal the anti-clockwise moment about the same axis. That is, this also states the same thing, with the exception that you have to first find the vertical component of such force. And then there are cases where you have three forces acting on an object. Now, in such, we call them the special cases, and there are three conditions you have to consider here. Now, the condition is that all the forces must lie on a plane. That's the first thing you have to consider in this case. All the forces acting on the object must be in the same plane, in the sense that you are not going to be looking at x, y, and z plane. It has to just be x and y. There's a different scenario we consider when you have to look at three types of planes: the x plane, the y plane, and the z plane. But in this case, it's just one plane. All of them must be on a two-dimensional basis. That's the first condition here. The second one is saying that their lines of action must intercept in a common point. And this leads us to what we studied earlier when we talked about the triangular moments. When we're looking at moments of triangular forces, we looked at the fact that you can represent the forces acting on an object in a closed triangle. And that's basically what this third one is telling you. It says the vector representing the forces can be arranged to form a closed triangle. You must recall the question we solved in that case, where we looked at a triangle like this, and then you see a force acting like this, another like this, and another like this. All of them intersect at a common point. So all the forces acting on an object must intersect at a common point if you are going to consider it to be at equilibrium when it is under the action of three forces. Now, these are all the conditions you must consider to solve problems when you have a body at equilibrium under the actions of non-parallel coplanar forces. Now, let us practice by solving some questions where we have forces that are non-parallel acting on the same object, and then let's see how we can resolve problems like that. Let's use those principles we just learned to solve this problem. We are told that a body of mass 10 kilograms is kept at equilibrium by two ropes as shown below. We have to calculate the tension in each rope, where this is tension 1 and then this is tension 2, and then this is the object, and the weight is acting downward in 10 kilograms, which would actually give us 100 newtons. Now let's make this into a vector diagram applying the triangle, as in the moment of a triangular forces. When we apply that, then we should be able to solve for tension 1 and tension 2. Now in this case, we see that we can take this as the reverse here, the vertical force, like this, okay? And then this still remains what we have here. Remember, this is now 100 newtons. Now this is acting in this direction, that is tension 2, right? And then tension 1. Look at the direction. we include all the directions just as we have here. So T1. Remember that this has to be 90 degrees, okay? Now what we have here is 40 degrees as shown. So if this is 90 and this is 40, that means this will have to be 50 degrees using the sum of angles in a triangle. Now that we have this, we can then begin to find any of this tension in the ropes. So all we have to apply is the sine rule. Now when we apply sine rule, we'll see that T1 over sine 40 degrees equals 100 newtons over sine 50 degrees, which is equal to T2 over sine 90 degrees. Please note that this is not the only method you can use to solve questions like this. And this works for no matter how the triangle looks anyways. But when you have a right angle triangle like this, you can also use your trigonometric ratio to solve for T1 or T2. You will always get the same answer. Okay? So first, let's solve for T1. To solve for T1, I'll focus on these two variables we have here, T1 over sine 40 and then 100 newtons over sine 50. And then that means that T1 equals 100 newtons multiplied by sine 40 degrees or divided by sine 50 degrees. Now let me quickly compute that with the calculator and see the final answer for T1. Now that will mean 100 multiplied by sine 40 and then the answer there divided by sine 50 degrees. And all together that gives us 83.91 newtons as the value of T1. Now let's find T2. To solve for T2, I will then use this part and this part. Since I already have T1 now, I will then say 83.91 newtons over sine 40 degrees equals T2 over sine 90 degrees. Now, we know that sine 90 is 1. So, ultimately, T2 is just 83.91 newtons divided by sine 40 degrees. That means T2 equals, let's see what we get with the calculator now. Now, we divide that by sine 40 degrees, and that will give us 130.54 newtons. So now we have the value of T1 as 83.91 newtons and the value of T2 as 130.54 newtons. And that's the solution to this question. Now let's solve this question. We are told that a uniform rod 5 meters long of mass 20 kilogram is pivoted at A. Now, a 10 kilogram mass is hung at end B, and then the rod is kept in equilibrium by a rope making 30 degrees with the rod at point C, which is 2 meters from point A. So as shown in this diagram, and then we have to calculate the tension in the rope. So we have to find the value of T here. Okay, now when we analyze what we have here, remember I mentioned that when you have a force acting at an angle like this, you have to find the vertical component. The vertical component here will be T sine 30 degrees. Okay? And then when we take pivot at A, all we have to do is apply clockwise moment equals anti-clockwise moment. So, taking moment at A. The clockwise moments are these 200 newtons and this 100 newtons. Now, in case you're wondering how did we get 200 newtons and 100 newtons here, the question itself mentioned that the rod itself is 20 kilograms and multiply that by 10, which we are taking to be the acceleration due to gravity, that will give you 200. And the same thing applies to the 10 kilogram mass here, multiplied by 10, and then you get 100. So that's how this came about. And don't forget that the distances have been given, the perpendicular distance to the pivot points. So that's all we need to apply. So taking moment at point A now, we will see that the clockwise moment 200 and then 100 will give you, that is 200 times the distance, that will be 200 multiplied by 2.5 plus 100 multiplied by the distance here is what? 5 all equals, now the anti-clockwise, t sine 30 multiplied by the distance here is 2. Now let's simplify. This will give us 500 plus, this is also another 500, equals, this will give you 0.5t times 2. Now what does this mean? 500 plus 500 will give us 1000. Okay, remember this is in newtons, equals 0.5 times 2 is 1. So we are left with t. So the value of t is therefore 1000 newtons. That is, the tension in this rope here, this particular rope here, is 1000 newtons. Try to solve this question from the 1994 UTME, which says the figure above shows a uniform wood of weight 200 newtons and length 50 meters. It is pivoted at one end and suspended at the other end by a cord at 30 degrees to the wood. Find the tension in the cord. Now you have this diagram to help you. So apply what you have learned so far in this video to solve this question, and then do compare your answer with what is gotten at the end of the video. Now don't forget, if you get the answer correctly, please ensure that you put it in the comment section saying I got it correctly. Now let's see if what you have solved is accurate. Now to solve this problem, what you have to consider is that the entire length of the wood itself is given as 50 meters, which means the weight is going to act at the middle. Since it is a uniform wood, the weight is going to be at the center here. So if this is 0 and this is 50 meters, it means this is 25. So if we are taking pivots at this point, the distance here is 25 meters, and the distance of this point to this end is the entire 50. And don't forget, you need to find the vertical component of the tension T here. This will be T subscript Y. That is the vertical component of the tension. So let's apply that. What will be the vertical component? T of Y is T sine 30 degrees. So when we want to take moment about this point, let's call this point A and then this point B. We then say taking moment at B, taking moment at point, let's take it at this pivot here, so that will be point A. What does that mean? We have to now look at clockwise and anti-clockwise moments. This will make the wood move in the clockwise direction, while T of Y will make it move in the anti-clockwise direction. So the clockwise moment will therefore be 200 newtons multiplied by the distance here, that's 25 meters. And all of this equals T of Y, that is T sine 30 degrees multiplied by the total distance here, which is what? 50 meters. Now let's resolve this. This, let me still keep it as 200 newtons multiplied by 25 meters. And then this will give me what? Sine 30 is 0.5. Multiply that by 50. And then we have 25 meters multiplied by T. So dividing both sides by 25 meters. Divide both sides by 25 meters. Okay? Let me show this clearly. 25 meters. You see 25 meters cancels 25 meters just as it does the same here. And then you see T is exactly 200 newtons. Don't forget, if you get 200 newtons exactly, put it in the comment section saying, I got the answer correctly. Now let us study the concept of center of gravity. Now, many of you should be able to do this. In my hand here is the calculator and here is my board marker. Now observe this. I'm going to place the marker at a point here, and you see how this calculator is balanced on the marker. Now some do this even with items such as a ball. If you should move this point to any point here, you see it begins to fall. It begins to fall, but there's a certain point where when you place it, it just seems to balance. No matter how you tilt it, it then begins to balance at that point. Once you place it like that, it remains balanced. The same thing happens when you have a ball and then you spin it on your finger. You just see that it seems to balance at a particular point. If you should shift your finger to the left or right, the ball spins off that finger. Now that point there is what we know as the center of gravity of the ball, or the center of gravity of my calculator in the case where I balance it on my marker like this. Now, how do we define the center of gravity of an object? Let's write that down. The center of gravity of an object is the point where the weight of the object is concentrated. And if you look at this definition clearly, you will see that what we just did actually follows the principle of moment. Now, we say that is the point where the entire weight of the object is concentrated. Now, the weight is not acting at the edge here, neither at this point, but at the center of gravity of this object. It doesn't matter how you put your marker, as long as it's at the center of gravity, you see it balances. Now, why does it balance? It's because the weight is acting downward and I'm able to give a reaction from the tip of this marker that is equal to the weight of the object. Now, when these two forces balances out, remember, when the force acting in one direction equals the force acting in the opposite direction. Now, in this case, the weight is acting downward, my reaction is acting upward. And the moment they balance out at the center of gravity, what happens? The reason why it has to be at the center of gravity is because that is where the entire weight is concentrated. So I have to give a reaction in the opposite direction of the weight of this object. Once those two balances out, this calculator will be in equilibrium position. So now you understand what center of gravity is and why it is important to principle of moment. So once again, if you're asked to define the center of gravity of an object, define it as the point on that object where the entire weight of that object is concentrated. Now that we can define it, let us try to find the center of gravity of some common objects, especially the ones that we use when we are solving problems on this topic. Now that we can define the center of gravity, let us look at the positions of center of gravity for some uniform shapes that we have around us or objects. In this case, we will be looking at the position of center of gravity for a uniform rod. Now, when we say a uniform rod, the position of center of gravity for a uniform rod like this is at the midpoint. This point here is your center of gravity. So it is at midpoint of the rod. So for example, if you have a meter rule and you are told it is a uniform meter rule, the position of the center of gravity is the midpoint of the 50 centimeter mark. Now, if it is longer than that, all you have to do is find the midpoint, and then that will be the position of the center of gravity. Now, for the purpose of practical, let me mention that not all meter rules you will find are uniform. So the way you can test for this is to try to balance it on a knife edge. You know that particular triangular shaped object we used in the physics lab to balance objects to see if it is at equilibrium, right? All you have to do is place your meter rule on it and find the point where when you place it on this knife edge, it balances horizontally, that it is suspended in air at least for a while. That will be the point where you have your center of gravity. Now, when you do this experiment, you will find some meter rule to balance at the 50 centimeter mark. In that case, those ones are uniform meter rules. But there are some you will see balancing at the 49.4, 49.5, sometimes 50.1, 50.2 centimeter mark. Those type of meter rules are not uniform. So for those ones, center of gravity is that point that balances horizontally on the knife edge. But whenever you are solving a question on principle of moment and you are told that the object is a rod or a meter rule and it is uniform, whatever be the length of that material, know that the center of gravity, which is the point where the entire weight of the object is concentrated, will be at the midpoint of that rod or meter rule. Okay, so that's for the case of uniform rod. Now, what if you are dealing with a uniform circular plate? Now, let me try to draw a circle. It's not perfect, but let's take it like that. Let's say you have a circular plate like this. There is a point on a circle known as the center of the circle. Now, how we define the center of the circle is a point that is equidistant to any point on the circumference. Meaning, if I should measure the length from this point to the circumference, it will be the same as measuring from this point to this on the circumference, as measuring from here to here on the circumference as well. So that will be the center of this circular plate. And at the same time, it serves as your center of gravity. This point here. Okay? This point is the center of gravity. If you have a uniform circular plate and you place it on a pin, it should balance horizontally. No matter how tiny it is, it should be able to stand horizontally on a knife edge if you place it at the center of gravity. And just like in this case too, if you should place a circular plate on a knife edge and it doesn't balance horizontally, just know that that's not where the weight is acting. You have to find the center of gravity, and it could be any point on this face, but it's always very close to the center. But when it is uniform, it is always going to be at the center. So if you are dealing with a circular plate where you are told the radius of the plate, you will know that the center of gravity is at that length from the circumference as well, the same as the radius. The distance from the center of gravity to the circumference is the same as what you know as radius of a circular plate. Now let us consider what happens when you are dealing with a uniform triangle or a uniform rectangle. Let us now look at how you can determine the center of gravity for a rectangular plate and a triangular plate. So if you have a rectangular plate like this, and you need to find the center of gravity, all you need to do is to draw the diagonals and find where they intersect. So this is a rectangular plate A, B, C, D. This will be our diagonal 1 all the way to C, and then diagonal 2 comes all the way to B like this. You see these points where they intersect? This particular point here is your center of gravity. So if you have to define this, it will be the point where the diagonals intersect. Serve as center of gravity. That's how you find it in the case of a rectangle. And it is the same procedure for a uniform triangle. Now in the case of a uniform triangle, let's take this as triangle ABC. What you need to do also is to draw your diagonals. Okay, and you see this point here is your center of gravity. So it's also point of intersection. Point of intersection of the diagonals is what serves as the center of gravity for a triangular plate. Now, just like in the case of the circular plate and a uniform rod, whenever you find any of these two shapes and then you place it on a knife edge and it does not balance at this point, you immediately know that such a shape is not uniform. Now what we call a uniform rectangle is such where the length are the same, they are parallel to each other and of equal length, just as the breadths are also parallel and of equal length, and the angles are 90 all apiece. All the angles are 90 degrees added together to give you 360. Now, in the case of a regular triangle or a uniform triangle, in this case, all the lengths are equal and all the angles are 60 degrees. If you find any such shape, the center of gravity can be determined by drawing the diagonals like this. But if you are dealing with a non-uniform shape of such, you place it on your knife edge and find the point where it balances horizontally, and that point is the center of gravity for each of those cases, whether it's a non-uniform rectangle or a non-uniform triangle. But this method helps you when you are dealing with regular rectangles or uniform rectangles and uniform triangle. Now let us learn how to determine the position of center of gravity for a regularly shaped object. So let's say you are in the lab and then you have an object that is irregularly shaped, something like this. Okay? It is irregular, so how can you find the center of gravity? All you need to do is pick 3 points near the edges of this shape. Ensure that those 3 points are far away from each other as possible. So I can pick this point here, pick this point here, and also pick this point here. Now what am I going to do? I will attach a plumb line to this point. Now, in case you don't have a plumb line, you can do this by just attaching a simple thread with a small weight at the end of that thread. Now, you suspend this vertically and allow that thread to swing freely under gravity. After a while, the thread balances and it will align itself along the path where the center of gravity is. Now, don't forget, every object concentrates their entire weight to the center of gravity. This we have already established. So that means after you allow this rest, it's going to balance along the path of the center of gravity. So in the case here, you might see that part going like this, and then this one might be going like this, and then this will be going like this, something like this. In that case, you see this point where they intersect. The point they intersect, let's call this point A, point B, point C, like this. You see this point where they intersect will be your center of gravity. The same thing applies even if you have something like this. Okay? It's also irregularly shaped. Just pick your point A, pick your point B, pick your point C, and find where your plumb line is going to rest. What this means is that I pick the shape up and then I balance it on A, allow it to rest, then I drop my plumb line. Wherever the plumb line rests on, that path is what I will trace out. Something like this. Let's assume that's the path. Then you turn the shape. Remember, you have marked the point. You can remove the rope now. And then you balance it at B. And then you watch where it is going to rest along. Something like this. So you mark that point as well. And then you do the same thing for C. And then you see C begins to go something like this. And then you see it all intersects at this point. This point here becomes your center of gravity. This is how you can determine the center of gravity of any shape, whether it is regular or irregular. It's very easy. It's just that when you are dealing with shapes such as a uniform rod, a uniform circular disc, a uniform triangle, a uniform rectangle, you don't have to go through all this stress. You already know how to find the center of gravity for such kind of cases. But there are cases like this where the shape is irregular. This practical method will help you determine the center of gravity, and then you can use that for all the applications for center of gravity. Let us now study the stability of objects. See, when it comes to stability of objects, there are 3 types of equilibrium we learn at this stage. Now, those equilibriums are named stable equilibrium, unstable equilibrium, and neutral equilibrium. Let us start with stable equilibrium. Stable equilibrium. Now, whenever you have an object, and then when you set the object down, it is stable because It is at equilibrium rather, meaning that it is not accelerating in any direction. You already know how to define equilibrium. Now you set up the object at equilibrium, it is balanced, it is not accelerating in any direction, and then you displace it slightly. Every time you displace such an object slightly, if it should always come back to that its original position it was at the beginning, then that kind of object is said to be at stable equilibrium. Let's define that. An object is said to be in stable equilibrium if it returns to its equilibrium position after being slightly displaced. Now you see these words are chosen carefully because even when an object is at stable equilibrium and you displace it with a high amount of force, there's tendency for it to find equilibrium at a new position. So that is why we say it is when you slightly displace it. So what this means is that you place the object and then it's at equilibrium, it is not accelerating, and then you just apply a small amount of force which displaces it a bit, and then it comes back to its original position. Then such an object is said to be at its stable equilibrium. Now in explaining this, I'll be using the same kind of object so that you can see that an object can be at stable equilibrium, the same object can be at unstable equilibrium and also at neutral equilibrium. Now in the case of stable equilibrium, let's look at some example. Now example, when you have a cone balanced on its circular base. Okay, that is when you have a cone like this that is balanced at this point. You see, when you place a cone like this, you see that it will remain balanced, right? What happens? If you push it with a small force in this direction, it tilts, giving you something like this. Then when you let it go, it will always come back to this. That tells you that this is its stable equilibrium position, because every time you displace it slightly, it will always return to this position. Okay, this is stable equilibrium. Another example would be a ball in a bowl. Now when you have a bowl like this and then there's a ball at the center here, now when you apply a force, what will happen? The ball will roll until it comes to this point and then continue like that, maybe to this point, and then in the end it will always find its way back to the center of the bowl like this. Just by displacing it begins to move about until it stops at the center, the same original position it was before you apply the displacing force. So you see here now that all these objects, these two objects we have mentioned here, always return to their original position after being slightly displaced. So that tells you their position known as the stable equilibrium position. Now let's look at what happened in the case of the unstable equilibrium. For unstable equilibrium, you see that when you place the object at this position, it is initially at equilibrium because it is balanced and it is not accelerating in any direction. But anytime you apply a force that slightly displaces such an object, you see that it will move further away from the equilibrium position. That is, it will go and balance itself away, it will fall away from that equilibrium position. Then that kind of object is said to be at unstable equilibrium. Let's define this. An object is said to be at unstable equilibrium, or in unstable equilibrium, in unstable equilibrium, if when displaced slightly, it moves further away from its original position. So that is, it is at equilibrium at a position, and then by the application of a slight force, it then moves further away from that original position. Then such position is known as the unstable equilibrium position. Now, an example of this is when you have, example, a cone resting on its apex vertex. Okay, that is when you have a cone like this, balanced at the top like this. Now, this takes a lot of patience and time to be able to achieve equilibrium at this point, but it is possible. Now, if you should apply any force at all on this, what will happen? It will fall away completely. Right? It means it moves further away from this equilibrium position completely. It does not return to it at all. This is a case of unstable equilibrium. Now, using the same example of a ball, now if you have an inverted ball, a ball on an inverted ball. Okay? So, you place the ball here, and then you apply a force. What will happen? You see that the ball will roll away completely from its original position. So this tells you that the ball at the top of an inverted ball is an example of unstable equilibrium. So now that we can describe unstable equilibrium, let us now go on to describe what is known as the neutral equilibrium. For neutral equilibrium, as we did in the previous cases, we start with the object at equilibrium in a position. Now, that is, the object is not accelerating in any direction. Now, when you apply a force that displaces it slightly, now I keep saying the word slightly because no matter what kind of equilibrium it is, if you should displace it with a high amount of force, you will always destabilize the object. Okay, so when you slightly displace an object that is in neutral equilibrium, what happens is that it will just move to a new equilibrium position. It will change to a new equilibrium position, and that's all. Remember, for stable, when slightly displaced, it comes back to its original position. For neutral, it will move away completely from its original position to a different position entirely. But for neutral, to just find a new point of equilibrium. That is how we define neutral equilibrium. But let's put it down. An object is said to be in neutral equilibrium if when it is slightly displaced it tends to move to a new position. Then that is neutral equilibrium. Now, for example, an example of neutral equilibrium is a cone resting on its slant side. Okay, now when you have a cone like this and then you apply a force, what happens? It will roll and find equilibrium at a new point like this. It just continues to roll like that, and it will always move to a new position where it is still going to remain balanced, that is at equilibrium. This is a case of neutral equilibrium. Another example is a ball on a smooth horizontal floor. So when you have a smooth horizontal floor like this and you place a ball here, by the time you apply a force, what happens? It rolls, finds equilibrium again. You apply force, it rolls, and then finds equilibrium at a new position. This is a case of neutral equilibrium. Now folks, if you do have any question on what we have covered so far on the topic of equilibrium of forces, we are open to all your questions. Just put it in the comment section and we promise to attend to all of your questions. And even if it warrants us making a video on it, we will definitely do that, just to ensure that you get the very best of understanding when it comes to all the topics that we deliver here on our channel. And if you are yet to be subscribed to the channel, kindly take a moment of your time, click the subscribe button. It's not going to cost you anything, it's just a click away. Click the button and then you become a member of the family. And for you to always get notified every time we put out a new video, I will advise that you click the notification bell icon. That way, YouTube will always notify you whenever we post a new video. And as we always say, we want to reach many students like you who need the kind of videos that we make here on our channel. And the way we can achieve this is if you continue to tell your friends about us. You can always do this by sharing our videos, ensuring that they see it on your own timeline. That way, they too can have access to the premium videos, educational content that we give out on this channel. So please share, please like, please comment, and let's keep making everyone better little at a time. Thank you so much for following the video so far. We continue to learn more in physics. I'll be seeing you in the next video. Bye for now.